Hi everyone, I'm Wei-Hong Li and I'm happy to be here to present our recent work on solving the imbalance problem in multitask learning. So multitask learning is to tackle a large variety of tasks within a single model, such that it achieves better overall performance on all tasks and less computation cost. However, there are at least two challenges in multitask learning. The first change is to design an architecture that shares only the relevant layers across the tasks and keeps the remaining layers task-specific. And the second challenge is to achieve good performance on all tasks, as multitask learning involves minimizing a set of loss functions for various problems with different difficulty levels, magnitudes, and characteristics, which will cause the imbalance loss optimization problem where one task dominates the remaining tasks. So we mainly look at the second challenge, and in this work, our goal is to design a multitask learning method to achieve a good performance on all tasks by addressing the imbalance loss optimization problem. In recent years, there was some work proposed to address the imbalance loss optimization problem, and they can be divided into two categories. The first category is the loss weighting approach that learns a weight per task loss for multitask learning optimization. And the second category is the parameter updating strategy. However, these methods only provide limited control on the parameters. So they still suffer from the problem of the tasks of one task dominating the remaining tasks, and they get lower task performance than the single task models in the standard multitask learning benchmarks. So in this work, we propose a knowledge distillation based method for multitask learning. And we introduce task-specific adapters to enable the multitask learning model to align the features of single task and multitask. And the experimental results show the efficacy of our methods on solving the imbalance problem in multitask learning. So in our method, given that single networks often perform well with sufficient training data, we hypothesize that the solution of the multitask network should be close to the single task ones and lie in the intersection of the single task solutions. To this end, we first train a task-specific model for each task in an offline stage and freeze the parameters. As shown in this diagram, our goal is to perform segmentation and depth estimation within a single network. Then we first train a segmentation network and a depth estimation network and freeze the parameters of these two networks. We then optimize the multitask learning model for minimizing a sum of all task-specific losses and for producing the same features with the single task networks. As shown in the right box of this diagram, we optimize the multitask learning model to minimize a sum of the segmentation loss and depth estimation loss, and to produce the same features with the segmentation network and depth estimation network. As the task-specific network compares different features, we introduce small task-specific adapters that map multitask features to the task-specific features. The adapters is shown in the right box in this diagram. In this way, the adapters align the features of the single task and multitask and enables a balanced parameter sharing across multiple tasks. We evaluate our methods on multiple multitask learning benchmarks. And here we just show the results on this NYUV2 as because of the time limitation. So this dataset contains RGBD indoor images, and each image is labeled for 3 tasks: the segmentation, depth estimation, and surface normal estimation. Here we show one example of the dataset. Here is the results on this dataset. We compare our method with the vanilla multi-task learning model using the uniformly weighting loss, and we compare our method with 3 recent loss weighting methods. A recent parameter updating strategy, the gradient surgery is also compared. So from the results, we can see the vanilla multi-task learning model achieve good performance, better performance on segmentation and depth estimation, while it obtains worse performance on surface normal compared with the single task learning model. This shows that simply applying uniform weighting to multi-task model cannot achieve good balance across tasks, and it suffers from the imbalance loss optimization problem. And we apply recent loss weighting methods to the multi-task learning model. We can see the grid norm achieve the best performance if we use the SegNet as the basic network architecture. This grid norm improves the overall performance, but it still suffers from the imbalance loss optimization problem, and it obtains worse performance on surface normal compared with the single task learning model. We compare with these methods, our method achieved the best results, best overall results, and better performance compared with the single task learning model on all the tasks. And these results kind of verify that our method enables the multi-task learning model to have a better balance parameter sharing across tasks, and thus achieve good performance on all the tasks compared with the single task model. And we also conduct aberration studies on this NYUV2 dataset. So as shown in the diagram, we use the output of the last shear layers for distillation loss. So the first question is to if we add more layers output for distillation loss, would it be helpful? So here we report the results of our method using the output of the last layer, or our method using the output of both the middle layer and last shear layer. So from the results, we can see using more layers output for distillation loss is helpful on this NYUV2 dataset. And we also observe that if we use a smaller network, then using the last shear layers output for distillation loss is sufficient. And the second question is aberration studies, whether these adapters is helpful. So we report the results of our method using the linear adapters or without the adapters. It's clear to see that without the adapters, the multi-task learning model is unable to achieve as good performance as our method using linear adapters, because it's really hard for the multi-task learning model to align the features with 3 different networks without the adapters. So the adapters introduced in this work help, enables the multi-task learning network to align the features between the single task and multitask. We also increase a bit the capacity of the adapters using the nonlinear adapters. So we show the results of our method using the linear adapters or nonlinear adapters. So from the result, we can see using linear adapters is sufficient. We will also release our code on our project page. All right, so that's all. Thanks for listening.